Somewhere in the archives of the most expensive machine humanity has ever placed above its own atmosphere, there is a file that nobody knows how to explain. It does not contain a galaxy. It does not contain a star, a nebula, a collision, a burst, or any of the violent, beautiful events that telescopes are built to hunt. It contains a piece of sky that was chosen precisely because nothing was supposed to be in it, and inside that emptiness, written into the way ancient light arrived at a gold-plated mirror 1 million miles from Earth, there is a shape, not a smear, not a blur, not the soft statistical fog that instruments produce when they are reaching past the limit of what they can resolve. A shape, structured, coherent, repeating, and geometrically clean in a way that nothing inside our cosmological models is capable of producing. The James Webb Space Telescope was built to look backward through time, toward the first light in creation, and in a patch of sky, catalogued as unremarkable, it appears to have found the imprint of something pressing in from outside the only universe we have ever known. Over the next couple of hours, we are going to walk all the way into that anomaly and out the other side. We are going to look at the fracture that was already spreading through modern physics years before Webb ever left the launch pad. A disagreement in the numbers, so stubborn and so precisely measured that it can no longer be called a mistake. We are going to descend into a cold patch of sky in the southern constellation Eridanus that has been sitting unexplained in the oldest map of the universe for more than 2 decades, while the field politely looked the other way. We are going to open a door that Albert Einstein left standing ajar in his own field equations, a door he neither wanted nor believed in, which permits the existence of surfaces in space where reality itself changes its mind about what the rules are. We are going to follow the mathematics of inflation into the place where it stops being a theory about our universe and becomes a theory about how many universes there are, whether we like the answer or not. And at the very end, we are going to arrive at a question that no telescope currently planned, funded, or imagined will ever be able to answer, and we are going to sit with the silence on the other side of it. If this is the kind of journey you want to be taken on, subscribe before we go any further, because these are the stories that get made when people stay. Now settle in, turn the lights down, let the room go quiet. Let's get into it. The first thing to understand about this discovery is that nobody was looking for it. There was no proposal, no hypothesis under test, no team with a theory to defend. There was a calibration field, and a calibration field is one of the most boring objects in professional astronomy. It is the equivalent of a blank sheet held up in front of a camera to check the color balance. Before an observatory can trust what it sees in the crowded, complicated, information-dense regions of the sky, it has to know exactly how it behaves when there is nothing to see. So it points itself at a region that has been surveyed before, catalogued before, cross-checked by multiple instruments across multiple decades, and confirmed to contain nothing of consequence along the entire line of sight. No cluster of galaxies bending light. No known concentration of dark matter. No dust lane. No foreground contamination. No gravitational structure of any kind. A control field. A blank page. A place where the answer is already known, so that the instrument can be measured against it. That is what this region was. It had been chosen for its emptiness the way a metrologist chooses a flat surface, not because the surface is interesting, but because its flatness is a known quantity you can measure other things against. Astronomers had looked at it before, with less capable eyes, and found precisely what the models said should be there, which was almost nothing at all, and had written it down and moved on. When Webb turned toward it, the expected result was already sitting in the operations plan. The infrared returns from that stretch of sky could be calculated in advance from its known contents. The background level was established. The galaxy counts at various distances were on file. Everything about the observation was a formality. The data that came back was not a formality. Buried inside the infrared returns, at a wavelength band where Webb's response is characterized more precisely than any comparable instrument in the history of the field, there was a pattern, not a rise in the background. Not a gradient sloping gently across the frame in the way that unmodeled foreground dust sometimes produces. A structured, coherent, organized distortion in the way light from far behind the field had arrived, and it was arranged in a geometry that matched nothing in the entire catalogue of known cosmic phenomena. The response was exactly what you would expect from professionals confronted with an impossible result, which is to say, they assumed immediately that they had broken something. The calibration sequence was run again. It produced the same output. It was run a third time under different conditions with different reference frames and different processing pipelines by different people who had not seen the earlier results, and the pattern held. The mirror alignment was checked segment by segment. The detector arrays were tested for correlated noise, for readout artifacts, for the specific families of error that infrared arrays are known to produce when they are pushed toward their sensitivity limits. Every interference source inside the solar system was accounted for and eliminated. Zodiacal light was modeled and removed. Thermal contributions from the telescope's own structure were checked against the engineering baseline and found to be nominal. The signal did not move, did not fade, and did not care. It was real, and nobody in the room had a name for it. To understand why that sentence carries the weight it carries, you have to understand what kind of machine produced it. The James Webb Space Telescope is not simply a larger version of what came before. That framing, which appeared in a great many launch week articles, badly misrepresents what it actually is. Hubble is a superb optical telescope in low Earth orbit that has spent decades returning some of the most consequential images ever captured. Webb is a fundamentally different category of instrument, built to solve a fundamentally different problem, and the problem it was built to solve is that the universe systematically hides its own history from anyone trying to look at it in visible light. Here is why. When a star ignites or a galaxy assembles, it radiates across the spectrum, much of it in visible and ultraviolet wavelengths. That light then begins a journey across an expanding universe, and the expansion is not merely a matter of things moving apart through space. Space itself stretches, and everything traveling through it stretches with it. A photon released 11 billion years ago has been riding an expanding fabric for 11 billion years, and its wavelength has been drawn out the entire way. Visible light slides toward the red. Red slides into the near-infrared. Ultraviolet drops down into the visible and keeps falling. By the time the earliest light in the universe arrives at our instruments, it has been pulled so far out of the range our eyes and our optical detectors are built for that it is not faint. It is invisible. It could be arriving in enormous quantities, and an optical telescope would register nothing whatsoever, because the information is simply no longer in the part of the spectrum that instrument can see. Every observatory before Webb ran into that wall in one form or another. Hubble could push astonishingly deep, and did, but it was looking through a keyhole cut into a much larger door. The deepest structures in cosmic history were not beyond its resolving power, they were beyond its spectral range. They were sitting in the infrared, and the infrared is where the story of the early universe is written. Building an instrument that can read that story requires solving a problem that sounds almost comic when you first hear it. Infrared light is heat. Any object with a temperature radiates in the infrared, and that includes the telescope itself. A warm telescope trying to detect faint infrared signals is like trying to hear a whisper from across a stadium while standing next to a running engine, except the engine is your own body and you cannot step away from it. To see the infrared universe, the instrument has to be colder than almost anything else in the solar system. So Webb was engineered around that constraint from the beginning. Its primary mirror spans 6.5 meters, built from 18 hexagonal segments of beryllium, a metal chosen because it holds its shape at cryogenic temperatures, where most materials warp. Each segment is coated in a microscopically thin layer of gold, because gold is an exceptional reflector in the infrared. The whole assembly was folded like origami to fit inside a rocket fairing, and then unfolded in space across weeks of single point-of-failure deployments, with each segment finally aligned to a tolerance measured in nanometers. a precision comparable to adjusting a surface the width of a country to within the thickness of a human hair. Behind the mirror sits a sunshield the size of a tennis court, 5 separate layers of a polymer film with vacuum gaps between them, each layer bleeding away heat from the one before it, until the cold side of the telescope sits at roughly 233 degrees below 0 Celsius. At that temperature, the instrument stops shouting over its own observations, and its detectors become sensitive enough to register the thermal signature of a bumblebee at the distance of the Moon. And it does not orbit the Earth. It sits at the second Lagrange point, 1.5 million kilometers out, a location where the gravity of the Earth and the Sun combine to produce a region of relative stability. From there, the Earth, the Moon, and the Sun all lie in the same direction, so the sunshield can block all three at once, while the telescope stares permanently outward into the dark with nothing warm behind it. All of that engineering exists for one reason, which is that when this telescope reports a pattern, the pattern is not an artifact. The whole architecture is a decades-long argument against the possibility of exactly the kind of error that would let you dismiss what it found in that empty field. And there is a second capability that matters here, one that is easy to overlook. Because infrared light passes through material that blocks visible light, Webb does not only see further, it sees through. Clouds of gas and dust that appear as solid black curtains in optical images are semi-transparent in the infrared. Webb can look into the interiors of star-forming regions, into the cores of galaxies, into places that were physically opaque to every previous generation of instrument. It reads a version of the sky that has been standing in front of us the entire time, unreadable, waiting for the right eyes. So when the anomaly appeared, the usual escape routes were closed. With an older observatory, a signal like this would have been dismissible on reasonable grounds. You could argue it sat at the ragged edge of the detector's sensitivity, that it lived down in the noise floor where instruments hallucinate, that the statistics were being pushed past what they could support. Those are legitimate arguments, and they have correctly killed a great many false discoveries. None of them applied here. The pattern was not marginal. It was sitting well above the noise, in a clean and thoroughly characterized part of the spectrum, in a field selected for the absence of anything that could contaminate it, produced by an instrument whose behavior, in exactly that regime, is understood better than that of any telescope ever flown. There was no instrumental exit. Something out there had left a mark on light that began traveling toward us when the universe was less than 3 billion years old, and Webb had finally been precise enough to notice. Now consider what that distance actually means, because it is the part that tends to slide past without registering. The region sits roughly 11 billion light-years away. The photons Webb collected departed their sources when the cosmos was in a completely different phase of its existence, an era of furious galaxy assembly, when the universe was younger than the Earth is now old, when there was no sun and no solar system and no planet on which anything would ever stand and look up. Those photons crossed a distance that has no honest human analogy, through an expanding void, for a span of time longer than the entire history of our star, and somewhere along that unimaginable crossing, something reached into them. Something organized them, something bent them along a curve, and then they carried that fingerprint the rest of the way to a gold mirror above the Earth, arriving at last in front of instruments precise enough to read it. The distortion is where the whole story turns. Light bending around mass is not exotic. It is one of the best understood phenomena in modern astronomy, and one of the cleanest confirmations general relativity has ever received. Mass curves space-time, light follows the curvature, and the result is gravitational lensing, an effect that has been measured around individual galaxies, around enormous clusters, around supermassive black holes, and around invisible halos of dark matter whose presence we know about precisely because of the way they bend the light of things behind them. The mathematics is settled, the profiles are catalogued. When astronomers see lensing, they can generally read the mass distribution that caused it the way a doctor reads a shadow on a scan. This did not read like anything on file. The deflection did not fall off with distance from a center the way it does around a concentrated mass. It was too even. It was spread across too wide an angular area. It was smooth in a way that mass simply does not produce, because mass is lumpy, and its lensing signature is lumpy, in a characteristic manner that the models reproduce with precision. This was not the signature of light curving around an object. It was the signature of light bending along a surface. There is a difference between finding a new example of a known thing and finding something that does not belong to any known category, and the second experience is much rarer and much more disorienting than the first. Imagine you have spent your career studying fingerprints on glass. You know the whorls, the arches, the loops. You can look at a print and say a great deal about the hand that left it. Then one day you are handed a pane with a mark on it that is not a fingerprint at all, that has no ridges, no pattern, no structure of the kind hands produce, but is nonetheless unmistakably the impression of something that was pressed against the other side of the glass. You have not found a new kind of finger. You have found evidence that the glass has another side. That is roughly where the team stood. They did what the discipline requires when reality misbehaves, which is not to speculate but to work. They flagged the observation. They documented every property of it, its angular extent, its radial profile, its spectral behavior, its position, and then they began the slow, unglamorous, absolutely essential process of trying to kill it, taking each conventional explanation in turn and testing whether it could account for what was in the data. That process consumed months. Every conventional explanation failed, and at some point in that period, in a conversation that has been described afterwards in slightly different ways by people who were present, somebody said the thing that everyone had been carefully constructing sentences to avoid saying. What if the source is not inside? Not inside the field, not inside the survey volume, not inside the observable universe, not inside the framework that every equation in modern cosmology was written to describe. Outside all of it. The room, by every account, went very quiet, because the appalling thing about that suggestion was not that it was absurd, it was that ruling it out was going to be much harder than anybody wanted it to be. Before we go any further into what Webb found, we have to be honest about what it threatens, and to do that, we have to give the standard model of cosmology its due, because it is genuinely one of the great intellectual achievements of our species, and it deserves better than to be treated as a straw man. It has a name that sounds like a filing code, which is part of why it never entered public consciousness the way relativity did. Lambda cold dark matter, 6 parameters. From those 6 numbers you can reconstruct the temperature pattern of the infant universe, the distribution of galaxies across the sky, the abundance of the light elements, the rate at which cosmic structure assembled, and the expansion history of everything. 6 numbers, and the universe falls out of them. The lambda is Einstein's cosmological constant, a term describing an energy that belongs to empty space itself, which turns out to dominate the energy budget of the cosmos. The cold, dark matter is the invisible scaffolding, matter that does not interact with light in any way we can detect, but which has mass and therefore gravity, and without which galaxies would fly apart and the cosmic web would never have assembled in the first place. Together, those 2 components, plus the ordinary matter that makes up everything we have ever touched, describe a universe that began roughly 13.8 billion years ago in a hot, dense state, expanded, cooled, forged hydrogen and helium, condensed into stars, gathered into galaxies, organized into clusters and filaments, and has been stretching ever since. And the reason cosmologists trusted it is not sentiment, it is prediction. This model told us what the cosmic microwave background should look like before we had instruments capable of measuring it properly. It specified the pattern of temperature fluctuations, the characteristic angular scale of the hot and cold patches, the relative heights of the peaks in the power spectrum, and when the satellites finally flew and returned data of sufficient quality, the predictions matched to a precision that made careers and won prizes. It told us the ratio of hydrogen to helium that should have been produced in the first minutes of cosmic history, a number that depends on nuclear physics and on the expansion rate in a very specific way, and observation confirmed it. It told us how galaxies should cluster at various scales, and the great galaxy surveys confirmed that too, including the faint acoustic signature frozen into the distribution of matter from pressure waves that rang through the primordial plasma before the universe was transparent. That is not a model that survives on faith. That is a model that repeatedly stuck its neck out and was repeatedly right. Cosmologists were not naive about it. Everyone knew there were gaps. Nobody knows what dark matter actually is at the particle level. Nobody knows what dark energy is at all. The physics of the very first instance remained speculative, but the foundation seemed solid, and the gaps looked like the kind of gaps that get filled in, rather than the kind that bring the building down. Then the numbers stopped agreeing with each other. The problem centers on a single quantity, the Hubble constant, which describes how fast the universe is currently expanding. It is one of the most fundamental numbers in cosmology. It sets the age of the universe and the scale of everything in it, and there are two independent ways to measure it. The first way looks backward. You take the cosmic microwave background, the oldest light in existence, released when the universe was around 380,000 years old, and cooled enough for atoms to form and photons to travel freely. That light carries a detailed imprint of the conditions at that moment. Feed those conditions into the standard model, evolve them forward across 13 billion years using the physics we believe governs cosmic expansion, and out comes a prediction for how fast space should be expanding today. That method gives a number of approximately 67 kilometers per second per megaparsec. The second way looks outward. You build what astronomers call a distance ladder. You start with objects close enough that their distances can be measured geometrically, by parallax, the same technique that lets your two eyes judge how far away a coffee cup is. Then you use those objects to calibrate a class of stars called Cepheid variables, which pulse in brightness on a rhythm that is directly tied to their true luminosity. Once you know how bright a star actually is and how bright it appears, distance follows. Then you use Cepheids in nearby galaxies to calibrate a class of supernova bright enough to be seen across the observable universe. Rung by rung you climb outward, and at the top, you measure how fast distant galaxies are receding right now. That method gives a number of approximately 73, 67 and 73. To anyone outside the field, that gap looks like a rounding error. Inside the field, it is a chasm. These are not sloppy measurements. Both methods have been refined obsessively for decades by teams who have every professional incentive to find errors in each other's work. The distance ladder has been rebuilt from the ground up more than once, with different calibrators, with independent parallax data, with entirely separate analysis pipelines. The early universe method has been checked against multiple satellites and multiple ground-based experiments. Alternative approaches have been brought in from outside the argument altogether. Gravitational lensing time delays, where light from a distant quasar takes multiple paths around a foreground mass and arrives at slightly different times. The tip of the red giant branch, a completely different stellar distance indicator with completely different systematics. Gravitational wave events used as standard sirens, where the waveform itself encodes the distance without any reference to the ladder at all. The gap does not close. It has been probed from every angle anyone could think of, and rather than shrinking under scrutiny, it has hardened. For a long time, the community treated this the way you would treat a leak, somewhere in the plumbing. Annoying, probably mundane, certainly something a sufficiently thorough team would eventually track down to a bad calibration or an unaccounted systematic in one of the rungs. That was the reasonable position, and it was held by reasonable people. Then, around the early 2020s, the discrepancy crossed the threshold that physics uses to distinguish a fluctuation from a fact, 5 sigma. In plain terms, that means the odds of a disagreement this large, arising by chance from measurement, scatter alone, fall to somewhere in the region of 1 in 3.5 million. That is the same standard used to announce the discovery of a new particle. It is the line at which the community stops arguing about whether a thing is real and starts arguing about what it means. So the Hubble tension is not an error, it is a property of the universe, and the standard model does not produce it. Sit with the strangeness of that for a moment. We have a framework that correctly predicts the temperature pattern of the infant cosmos to extraordinary precision. Using that same framework, we run the tape forward and ask how fast space should be expanding today, and we get an answer that is definitively, measurably wrong. The model that describes the beginning cannot correctly describe the present. Something happened between then and now, or something is missing from the accounting, or something outside the accounting is exerting an influence the equations have no term for. That was the state of things before Webb launched. The foundation was cracked, but there was still a defensible argument that the repair would be an internal one, a missing component in the early universe, some form of energy that acted briefly and then faded, a subtle modification to how dark matter and dark energy interact. Uncomfortable, but fixable from inside. Then Webb went to work, and instead of easing the pressure, it added to it from an entirely unexpected direction. The telescope had been built in significant part to observe the first galaxies, and the expectation was reasonably clear. In the standard picture, the earliest galaxies should be small, chaotic, and primitive, loose clumps of gas collapsing into the first generations of stars. Irregular, disordered, chemically pristine, still in the process of becoming anything. Structure takes time. Disks need many rotations to settle. Spiral arms require a stable, ordered, rotating disk to form in. Heavy elements require generations of stars to live and die and seed the surrounding gas. The clock allows only so much of that in the first few 100 million years, and the models were confident about how much. Webb looked and found galaxies that had not read the models, objects at enormous redshift, meaning objects seen as they were when the universe was a few % of its current age, presenting as far too developed, well-formed disks, ordered rotation, structures that in some cases show signs of spiral organization, masses in stars that should have required substantially longer to assemble than the available time permits, chemical enrichment implying that generations of stellar life and death had already run their course when the universe had barely begun. The reaction was, initially, entirely appropriate skepticism. Early redshift estimates based on photometry can be wrong, and some of the first sensational candidates did indeed turn out to be lower redshift interlopers once spectra were obtained. But as spectroscopic confirmations accumulated, the pattern did not dissolve. Enough of the objects were real, at the distances claimed, with the properties reported. The universe was building large, organized, mature structures faster than the standard model says it should be able to. There are ways to soften this. Perhaps star formation was more efficient in the early universe than assumed. Perhaps the first generation of stars was much more massive, burning brighter, and skewing our brightness to mass conversions. Perhaps the dust content is different, altering how we read the light. These are serious proposals and some of them may well be right, but every one of them is a patch, and the number of patches required to hold the picture together has been growing rather than shrinking. And now, layered on top of all of this, was a signal in a calibration field. A geometrically impossible distortion sitting in a piece of sky that had been selected for containing nothing at all. The model was no longer merely cracked in one place. It was under simultaneous pressure from the expansion rate, from the timeline of structure formation, and from an anomaly in the geometry of space itself. And the possibility that serious people were now obliged to put on the table, however much they disliked it, was that the source of the strain might not be located anywhere inside the model. It might be coming from outside it. That word, outside, needs to be handled carefully, because it is doing something unusual here. In ordinary usage, outside means beyond a boundary in space, outside the building, outside the city. But the universe is not an object sitting inside a larger emptiness with a surface you could walk up to and touch. When cosmologists talk about something being outside our universe, they mean something considerably stranger and more precise. They mean a region of space-time that is not causally connected to ours, a region that no signal from us has ever reached, and no signal from which has ever reached us, not because it is far away in the ordinary sense, but because the structure of space-time between us forbids the crossing. Something that is outside in that sense should be permanently invisible. That is very close to the definition. And yet the entire premise of what follows is that something outside may have left a mark on the inside. Which sounds contradictory until you look at how the mathematics actually handles boundaries. Because a boundary is not the same as the thing beyond it. You cannot see through a wall, but you can absolutely see the wall. And if the wall carries energy, if it curves the space around it, if it exerts a gravitational influence on everything nearby, then the wall is not outside at all. The wall is the last thing that is still inside, the final page of our universe, and it is entirely capable of leaving a fingerprint on light that passes near it. That distinction is the hinge on which this whole story turns. We are not talking about seeing another universe. We are talking about seeing the edge of ours and inferring from the shape of that edge that it is an edge and not simply an end. To a cosmologist, no two patches of sky are equivalent. The sky is not a uniform backdrop, but a landscape with terrain, and part of the training of anyone who works in this field is learning to read that terrain before deciding where to point anything. Some regions are crowded. Galaxy clusters sit at the intersections of the cosmic web. Thousands of galaxies bound together by gravity, warping the space around them so severely that background objects appear stretched into arcs and rings, and sometimes multiplied into several images of the same source. These are spectacular and they are useful, but they are noisy in the specific sense that everything in front of you is doing something to the light behind it. Other regions are voids, vast underdense bubbles that can span hundreds of millions of light years, where galaxies are sparse, and the background radiation runs marginally cooler than average, because photons lose a small amount of energy climbing out of the region as it expands beneath them. And then there are the quiet fields. These are the patches astronomers reserve for work that requires a clean baseline, low foreground dust, no significant structure along the line of sight, well-measured background, catalogued galaxy counts at every distance interval. A quiet field is not merely a place where you expect to see little, it is a place where what you will see has already been calculated, which is a completely different and much more powerful condition. That is what makes the anomaly so difficult to dismiss. The field was not chosen at random and then found to be strange. It was chosen because its contents were already known to a level of detail that made it useful as a reference standard. And then something appeared inside it that had no business being there. At the relevant distance, in that specific direction, the standard model places nothing, no catalogued supercluster, no known filament crossing the sightline, no void boundary, no concentration of dark matter dense enough to produce a measurable lensing effect. The large-scale structure surveys, those three-dimensional maps of how matter is distributed across the observable universe, show that stretch of space as close to uniform. And uniform means featureless, and featureless means there should be nothing present with sufficient mass to bend anything. The light was bent anyway, precisely, coherently, and with a structure that is the single most important detail in this entire account. So let us be exact about what the shape actually is, because everything else depends on it. The measurement technique involved is called weak gravitational lensing, and it is one of the most elegant things modern cosmology does. Strong lensing, the dramatic kind, produces obvious arcs and multiple images, and is confined to regions of extreme mass concentration. Weak lensing is everywhere, and it is almost invisible. As light from a distant galaxy travels toward us, it passes through the gravitational fields of everything along the way, and each encounter tugs the path very slightly. The cumulative effect is that the galaxy's apparent shape is distorted by a fraction of a percent, stretched very slightly in a direction determined by the mass distribution it passed. You cannot detect that in a single galaxy. Galaxies come in every shape imaginable, and there is no way to know what any individual one looked like before the light was interfered with. But galaxies are not intrinsically aligned with one another. Their orientations on the sky should be random. So if you measure the shapes of tens of thousands of background galaxies across a region, and find that their apparent orientations are not random, that they are systematically stretched in a coherent pattern across the field, you have detected the gravitational influence of everything that lies between them and you. And crucially, you can invert the pattern. From the distortion, you can reconstruct the distribution of mass that produced it, including mass that emits no light at all. This is how the dark matter maps you have seen were made. It is one of the very few techniques we possess for weighing the invisible. When the team applied this reconstruction to the anomalous field, the mass distribution that came out did not correspond to any structure in the catalogue. It was not a cluster. A cluster produces a mass concentration that peaks sharply at a center and falls away steeply with radius, the signature of many objects bound together in a gravitational well. The reconstruction showed no such peak. It was not a filament. Filaments produce elongated distortion patterns aligned with the filament's axis, a directional stretching that reflects the fact that the mass is arranged as a thread. The signal was not elongated. It was close to circular in projection. It was not any known configuration of dark matter either. Dark matter clumps. It forms halos. It forms the connecting threads between them, and the way it distributes itself is one of the best tested outputs of large-scale structure simulations. Nothing in the standard picture arranges dark matter into a smooth, extended, evenly distributed sheet at this scale, without a corresponding concentration of ordinary matter to mark it. What the reconstruction showed was a surface, a plane, oriented roughly perpendicular to our line of sight, extending across the field. The lensing strength was highest toward the center of the region and fell away toward the edges with a smooth, gradual profile, with none of the sharp cutoffs and steep gradients that a localized mass concentration produces. The light was not curving around something, it was bending as it crossed something. Several of the physicists who examined the reconstructed profile independently, before any of them had compared notes, reported the same instinctive reading. It looked like a wall, not a wall made of matter, not a wall made of anything with a name in the periodic table or the particle catalogue, a boundary, a place where the properties of space on one side differ, subtly but genuinely, from the properties of space on the other, and where the transition between the two carries energy and therefore curves space-time and therefore bends light. Nobody wanted to be the first to say the obvious thing about what a boundary between two regions of space with different properties would actually be. But the geometry was already saying it. There is a specific quality to the profile that makes the conventional explanations so difficult to sustain, and it is worth being precise about it, because this is exactly the sort of detail where a scientific claim either holds or falls apart. General relativity tells you exactly how light should behave near mass. The deflection angle depends on the mass and on how close the light passes, and it falls off with distance in a manner that has been confirmed at every scale, from the sun's limb during a solar eclipse to the largest bound structures in the universe. Every lens ever mapped obeys this. It is not a rule of thumb. It is a direct consequence of the field equations, and it does not bend to convenience. A mass concentration of any kind at any scale produces a lensing signal with a characteristic radial dependence, strong near the center, weakening rapidly outward, with the rate of weakening determined by how the mass is distributed. You can be sophisticated about it and model complicated mass distributions, and you can produce a considerable variety of profiles that way, but there is a flaw to how flat you can make it, because the signal must ultimately trace back to matter, and matter is concentrated. An extended surface is a different geometry entirely. If the source of the curvature is not a lump but a sheet, then the fall-off is governed by the geometry of the sheet rather than by the fall-off of a mass density, and you get a profile that is far flatter and far more extended than any concentration can produce. That is the signature that appeared, not merely unusual, structurally distinct from the entire family of mass-based lensing profiles. And it happens that this exact profile had already been written down in the theoretical literature years before Webb launched, by people working on something that most of their colleagues considered unfalsifiable speculation. They had calculated what a domain wall would look like, a surface across space where a fundamental field changes its value from one stable configuration to another. They had derived the energy density such a wall would carry, the way that energy would curve the surrounding spacetime, and the specific lensing signature it would imprint on background light. Circular in projection when viewed face-on, smooth radial fall-off, no central peak, no sharp edges, extended across a large angular scale. The predictions sat in journals, largely unread outside a small community, waiting for an instrument sensitive enough to test it against reality. That is the situation. And this is where the story stops being about a telescope and starts being about the mathematics that has been quietly insisting for over 40 years that our universe cannot possibly be the only one. But before we go there, one more thing must be said about the signal itself, because honesty requires it, and because the story is more interesting when told straight. The match to the domain wall prediction is a match within current measurement uncertainty. That phrase is not a technicality to be brushed past. Cosmological measurements at these distances carry substantial error bars. The reconstruction of a mass distribution from galaxy-shape statistics is a statistical procedure, not a photograph. And the theoretical models being compared against have free parameters that can be adjusted, which means that a fit, however good, is worth less than it appears if the model was flexible enough to fit almost anything. So what we have is not proof. What we have is a signal that is inconsistent with every conventional structure in the catalogue, and consistent with a profile that was predicted in advance by a framework that had no observational support at the time it made the prediction. In science, that is not a conclusion. It is the beginning of an argument, and it is the specific kind of beginning that has historically preceded the discoveries that mattered. The word multiverse has been so thoroughly worn down by use that it barely functions as a technical term anymore. Film franchises have used it as a device for bringing back actors. Novels have used it as a way of having the ending both ways. It has come to signal, in ordinary conversation, a kind of unserious cosmic escapism, the intellectual equivalent of shrugging. Strip that away, and something entirely different is underneath. The multiverse, in the sense that matters here, is not a creative flourish, and not a philosophical preference. It is an unwanted consequence. It falls out of the most successful theory of the early universe anyone has ever constructed, and the physicists it falls out on have spent 4 decades trying to find a way to avoid it, and have not succeeded. That theory is inflation, and to understand why it forces the conclusion it forces, you have to understand first why anyone believes it. Inflation says that in the first sliver of a second after the beginning, before the universe was old enough to be measured in any unit that means anything to us, space underwent a period of expansion so violent that everything afterward looks stationary by comparison. Not fast. Exponential, a region smaller than a proton, inflated to something like the size of a grapefruit, and kept going, doubling and doubling and doubling. In a span of time you would have to write with more than 30 zeros after the decimal point before reaching a digit that was not 0. That sounds like an extravagant thing to propose, and the immediate question is why anyone would. The answer is that inflation solves 3 separate problems in cosmology that have no other satisfactory solution, and it solves them all at once with a single mechanism, which is the sort of thing that makes theorists sit up. The first problem is the uniformity of the sky. Look in one direction with a microwave telescope and measure the temperature of the cosmic background. Then turn around and look in the exact opposite direction and measure it again. The 2 temperatures agree to within 1 part in 100,000. That should be impossible. Those 2 regions are on opposite sides of the observable universe. In a universe expanding at any ordinary rate, no signal, no particle, no influence of any kind could ever have traveled from one to the other in the entire history of the cosmos. They have never been in contact. 2 objects that have never interacted have no reason to be at the same temperature, in exactly the way that 2 kettles in 2 different houses have no reason to agree unless something connected them. Yet the sky is uniform to a precision that demands an explanation. Inflation supplies one. If everything we can see was, before inflation began, a single tiny patch, small enough to have equilibrated internally, then it was all in contact, it all reached the same temperature, and then inflation blew that patch up to a size far larger than our observable universe. The uniformity is not a coincidence. It is a memory of a time when everything was touching. The second problem is flatness. The geometry of space, on the largest scales, can in principle be curved in either direction, like the surface of a sphere or like a saddle. Measurements say it is flat, or so close to flat that we cannot distinguish it from flat. That is an extraordinarily delicate condition. Curvature grows over time in an expanding universe, so for space to appear flat now, it must have been flat to an almost absurd degree in the beginning, tuned to dozens of decimal places for no apparent reason. Inflation dissolves the problem entirely. Take any surface and stretch it enormously, and the region you can see becomes flat, in the same way that the ground beneath your feet appears level despite standing on a sphere. Flatness is not a coincidence either. It is a consequence of stretching. The third problem is the most impressive, because inflation does not merely explain an existing observation. It made a prediction that was subsequently confirmed in detail. If inflation happened, then quantum fluctuations, the irreducible jitter that quantum mechanics imposes on any field, would have been present in the inflating region. Those fluctuations were microscopic. Inflation stretched them to cosmic dimensions and froze them in place. They became slight variations in the density of matter, and those variations became the seeds around which everything gravitationally assembled. Every galaxy, every cluster, every filament of the cosmic web, every star, and every planet traces its ancestry back to a quantum ripple that got caught in an expanding universe. Inflation predicted the statistical properties of that ripple pattern, its distribution across angular scales, its near but not exact uniformity. When the satellites measured the microwave background in detail, the pattern matched. So inflation is not fringe, it is the leading framework for the earliest moments of cosmic history. It is supported by multiple independent lines of precision measurement, and it is taught as the standard picture. The trouble is entirely in what comes with it. Inflation requires a field. Fields are the fundamental objects of modern physics, and every particle we know about is an excitation in one. The field responsible for inflation is called the inflaton, and it has an unusual property. When it sits at a high value, its energy behaves in a way that causes space itself to expand exponentially, rather than causing things within space to move. It is not that matter was flung outward. It is that the container grew, everywhere, at once. For inflation to end and produce a universe like ours, the inflaton must decay, dropping from that high-energy state into a lower one, and converting its energy into the hot, dense soup of particles and radiation that we call the Big Bang. Inflation ends, ordinary expansion begins, matter condenses, and 13 billion years later, somebody builds a telescope. That is the picture. And here is where quantum mechanics walks in and refuses to leave. Quantum mechanics is not a peripheral concern that can be handled later. It is the most exhaustively verified theory in the history of science, confirmed to more decimal places than any competing framework has ever managed, and no experiment has ever caught it out. And quantum mechanics says that the decay of a field is not a deterministic process that happens everywhere at once on a schedule. It is probabilistic. It happens here and not there, now and not yet, according to probabilities rather than certainties. So the inflaton field does not switch off across all of space simultaneously. In some regions it decays early, inflation ends, and a universe forms. In other regions it lingers. And in those lingering regions, inflation continues, which means space there is still expanding exponentially, which means those regions are producing new volume at a staggering rate. Follow that logic to its conclusion. The regions where inflation ends stop growing exponentially, and settle into ordinary expansion. The regions where inflation continues keep doubling, which means that the still inflating volume grows faster than the decayed volume can ever catch up. No matter how many pockets stop inflating, the inflating background between them is expanding faster than they can consume it. Inflation, once it starts, never stops. Not globally. It stops locally, in patches, over and over, forever, while the space between those patches goes on inflating without end. This is called eternal inflation, and it is not an exotic variant of the theory tacked on by enthusiasts. It is what standard inflation does when you take quantum mechanics seriously, which is not optional. Every patch where inflation ends is a bubble. Inside each bubble, the inflaton has decayed, energy has converted into matter and radiation, and a universe is unfolding. Between the bubbles, the background continues to inflate, driving them apart faster than anything inside them could ever cross the gap. Each bubble is causally sealed, not distant, sealed. No signal from inside one can reach inside another, because the space between is expanding faster than light can traverse it. Our universe, in this picture, is one of those bubbles. Everything we have ever observed, every galaxy and every survey, the entire 13.8 billion year history of everything, is the interior of a single pocket where the inflaton happened to decay at a particular moment, inside a background that has been inflating without interruption since before that moment and is inflating still. And the number of bubbles is not finite. The process has no stopping condition. Eternal inflation generates them without limit, forever, into a future with no end. This is the point that people find hardest to accept, and the reason for the resistance is understandable. It sounds like the sort of thing a theory produces when it has been extrapolated well past the domain where anyone should trust it. But the extrapolation is not optional. If you accept inflation, and the evidence for inflation is substantial, and you accept quantum mechanics, and there is no serious alternative to accepting quantum mechanics, then eternal inflation follows without any additional assumptions. Nobody chose it, nobody wanted it. Several of the people most responsible for developing it have been publicly uncomfortable about where it leads. The mathematics simply does not offer an exit. Now we arrive at the part that connects all of this back to a telescope and a piece of empty sky. Bubbles do not nucleate in a neat grid with generous spacing. They form randomly throughout the inflating background, wherever the field happens to decay, and once formed they expand. Their walls race outward at close to the speed of light, while the background between them inflates. In most cases, the inflating background wins the race, and the bubbles are separated forever, drifting apart faster than they can grow toward each other, never to interact. But not always. If two bubbles nucleate close enough together, close enough that their expanding walls can meet before the inflating space between them drives them apart, then they collide. And a collision between two universes is not a small event. In the high-energy cases, the meeting is catastrophic. The wall of one bubble slams into the wall of the other, and the energy released destroys the structure of both interiors near the impact zone. Nothing survives there in any recognizable form. But collisions come in a range, and the interesting cases are the gentle ones. If the energy difference between the two bubbles is small, if the collision occurs far from where you happen to be, if the geometry is favorable, then the result is not annihilation, it is a mark, a region where the curvature of space-time is subtly altered, a disturbance propagating inward from the point of contact, weakening as it travels, arriving eventually as a faint distortion in the geometry of a region billions of light-years across. And at the interface, where the two bubbles are pressed against one another, there is a surface, a boundary where the inflaton field, or one of its descendants, transitions from the value it settled into in our bubble to the value it settled into in the neighbor. That transition region carries energy. Energy curves space-time. Curved space-time bends light. The theorists calculated what that would look like from the inside, from a vantage point within one of the colliding bubbles, looking out toward the boundary. They derived the profile, extended, smooth, circular in projection, flatter than anything a mass concentration could produce. They published it. And then they waited a very long time for anyone to be able to check. There is a much older anomaly in this story, and it has been sitting in plain view, unexplained and quietly awkward, for more than 20 years. The cosmic microwave background is the oldest thing anyone can look at. It is the light released when the universe cooled sufficiently for electrons and protons to combine into neutral hydrogen, roughly 380,000 years after the beginning. Before that moment, the cosmos was an opaque plasma, and light could not travel freely. After it, the universe became transparent, and the photons released at that instant have been traveling ever since. They fill the entire sky in every direction, arriving from all sides, a faint microwave glow that is the single richest source of cosmological information we possess. It is not perfectly smooth. It carries fluctuations, temperature differences from place to place, on the order of 1 part in 100,000, and those fluctuations are the imprint of the density variations that later became everything. 2 satellites in particular, WMAP and then Planck, mapped this pattern across the whole sky with increasing precision, and the statistical properties of what they found match the predictions of inflation with a fidelity that is genuinely remarkable. The distribution of hot and cold regions across angular scales, the characteristic size of the patches, the way the power is spread across the spectrum, all of it consistent with a universe seeded by stretched quantum noise, almost all of it. In the southern sky, toward the constellation Eridanus, there is a region that is colder than it should be, not marginally colder in a way that could be shrugged off, roughly 70 microkelvin below the average, spread across an angular patch about 5 degrees wide, which is 10 times the apparent width of the full moon. In the context of a map where the entire dynamic range is measured in tens of microkelvin, that is enormous. It is the single largest deviation in the oldest picture of the universe we have. It was flagged in 2004. It has been the subject of continuous investigation ever since, and it has never been satisfactorily explained. The first candidate was a supervoid. If there were an enormous underdense region between us and the surface where that light was released, then photons crossing it would lose a small amount of energy on the way through, arriving slightly cooler. The mechanism has a name, the integrated Sachs-Wolf effect, and it is well understood. As a photon falls into a void, it gains energy, and as it climbs out, it loses energy, and in a universe where expansion is accelerating, the void grows shallower during the crossing, so the climb out costs slightly more than the fall in gave. Cross a big enough void, and you emerge measurably cooler. In 2015, a survey identified a large underdense region in the direction of the cold spot. For a period, it appeared the problem was solved, and a number of review articles treated the matter as closed. It was not solved. When the calculation was performed carefully, using the measured properties of the void rather than a generic model, the effect it could produce fell far short. The void was real, but it was too small and too shallow to account for more than a fraction of the temperature deficit. Subsequent surveys of the region found the underdensity to be less pronounced than initially estimated, which made the shortfall worse rather than better. The cold spot remained larger than anything on the sightline could explain. The second candidate was that the cold spot is simply a rare fluctuation. In a random field, unusual features occur. If you draw enough samples, some of them will be extreme. Under this reading, the cold spot is a 1 in a few hundred outcome that requires no new physics at all, and looking for a special explanation is the same error as being astonished that somebody, somewhere, won the lottery. This is a defensible position, and it was the one most frequently cited in the literature. It is also the one that resolves the least, because it amounts to declaring the anomaly uninteresting, and it has a specific weakness, which is that the cold spot was not found by scanning the map and picking out the most extreme feature. Its statistical significance depends on how the search was conducted, and this is a genuine subtlety that the field has argued about at length. But the feature's morphology, the way its temperature profile behaves across its boundary rather than merely its depth, is harder to accommodate as ordinary noise than its amplitude alone. The third candidate appeared in print only occasionally, but circulated in conversation considerably more freely than the publication record would suggest: a bubble collision imprint. The mathematics of bubble universe collisions makes a specific prediction about what such an event would leave in the microwave background. Not a random patch, a roughly circular region offset from the center of the sky with a particular temperature profile that varies in a characteristic way from the middle outward to the rim. The circularity comes from the geometry of two spherical surfaces intersecting. The profile comes from the dynamics of the collision itself. The cold spot is roughly circular. Its temperature behavior across the boundary shows features that are consistent with what the collision models describe. The resemblance has never been exact enough to constitute a confirmation, and the models have enough flexibility that a good fit is worth less than it looks. But it has also never been wrong enough to close the door, so the cold spot sat there, listed in anomaly catalogues, mentioned in review papers under headings about unresolved features, not denied, not explained, and not, for the most part, discussed in polite company. And then Webb, using a completely different technique, measuring a completely different physical effect, looking at a completely different part of the sky, found an anomaly that pointed toward the same class of explanation. Two independent observations, separated by billions of light years and by every methodological choice that could separate them, converging on the same interpretation. Something had touched our universe from outside, and it had left more than one mark. Now we should talk about Einstein, because there is an irony here that is too good to leave out. Albert Einstein would have found the multiverse repugnant. He spent the final decades of his life pursuing a unified theory, a single coherent mathematical structure from which all of physical reality would follow. He resisted quantum indeterminacy his entire career. The idea that reality might be fundamentally plural, that there might be innumerable universes with innumerable different sets of laws, and no principle selecting ours, would have violated everything he believed physics was for. And yet the door is in his equations. He put it there without meaning to, and he could not take it out, because mathematics is frequently more honest than the people who write it. General relativity describes how matter and energy curve space-time, and how curved space-time in turn dictates the motion of matter and energy. It is expressed as a set of 10 coupled equations relating the geometry of space-time to the distribution of energy within it. Their success is difficult to overstate. They predicted the bending of starlight around the sun, confirmed during the eclipse of 1919 in the observation that made Einstein internationally famous overnight. They predicted black holes decades before anyone had evidence they existed. They predicted gravitational waves a full century before instruments sensitive enough to detect them were built. And when those instruments finally recorded a signal from two colliding black holes, the waveform matched the predictions so closely that the analysis was almost anticlimactic. But the field equations do not describe only the universe we happen to inhabit, they describe a family of possible spacetimes, and we identify ours by supplying additional information about what is in it and how it started. The equations themselves are more permissive than the reality they were written to capture. They admit solutions that nobody expected, and some that nobody wanted, including configurations describing more than one connected region of space, and geometries in which a boundary between regions is not an artifact of the coordinates, but a physical surface with physical properties. One family of these solutions is precisely what we need here. They are called domain walls. The concept comes from particle physics rather than cosmology, and it is easier to grasp than its name suggests. Fields can have more than one stable configuration. Picture a landscape of hills and valleys, where the height represents energy, and a ball rolling on that landscape represents the state of the field. The ball will settle into a valley, because that is where the energy is lowest. But if there are several valleys of comparable depth, then which one it settles into is a matter of where it happened to be when it lost momentum, and there is no reason for the same choice to be made everywhere. So one region of space settles into one valley, and a distant region settles into a different one. Between them, there must be a transition. The field cannot jump discontinuously, so there is a zone where it climbs out of one valley, crosses the ridge, and descends into the other. In that transition zone, the field is at higher energy than in either valley, which means the transition zone carries energy, which means it has mass, which means it gravitates. That is a domain wall, a surface stretched across space, marking where the universe made one choice on one side and a different choice on the other, carrying real energy and exerting real gravitational influence. Einstein's equations accommodate them without complaint. Extensions of the standard model of particle physics produce them naturally. Analogous structures show up in condensed matter physics, in magnetic materials, where regions of aligned spins meet regions aligned differently, and the boundary between them is a physical, measurable, energetically costly thing. And now put the two ideas side by side. Two bubble universes, each formed when the inflaton field decayed into a particular configuration, each having settled into a slightly different valley of the energy landscape, pressed up against one another after a collision. The boundary between them is, mathematically, a domain wall. A domain wall stretched across billions of light years would bend light. It would bend it smoothly, along an extended surface, producing a lensing profile flatter and broader than any concentration of mass can generate. Exactly the profile in Webb's data. Einstein did not predict this. He would have hated it. But he left the door open in the mathematics, and the mathematics does not care whose name is on it. When physicists took the measured lensing profile and asked what configuration of space-time geometry would produce it, the answer that came back was not a galaxy cluster, not a dark matter halo, and not a void. The answer was a wall. Science does not leap to extraordinary conclusions, and the reason is not caution for its own sake. It is that extraordinary conclusions are almost always wrong, and the discipline has been burned often enough to have built a procedure around it. The procedure is unglamorous. You list every known phenomenon capable of producing an observation resembling the one you have. You test each against the data. You eliminate the ones that fail, and whatever survives, however unwelcome, is what you are left holding. The team ran that procedure on the Webb signal exhaustively over a period of months. It is worth walking through it candidate by candidate, because this is the part that determines whether anything else in this story deserves attention. The first candidate was an uncatalogued galaxy cluster on the line of sight. Clusters are the largest gravitationally bound structures in existence, and they are powerful lenses. Some are difficult to detect, optically, buried behind dust, or at awkward redshifts where surveys are incomplete. Could a cluster be hiding in the foreground, producing the distortion? This one is almost self-refuting, because Webb is the instrument you would build specifically to find such a cluster. Galaxy clusters are full of hot gas that radiates strongly in the X-ray and produces characteristic emission across the infrared. The member galaxies themselves are luminous. A cluster massive enough to generate the observed lensing would be one of the most conspicuous objects in that part of the sky, and it would be conspicuous in exactly the wavelengths where Webb is most sensitive. The region was examined across every available band. It was clean, there was no cluster, and the mass required to produce the signal could not possibly hide from an instrument of this capability at this distance. The second candidate was a dark matter filament. The cosmic web is threaded with these long diffuse concentrations of dark matter and gas connecting the dense nodes where clusters form. Filaments do lens light, more weakly than clusters but measurably, and they are genuinely hard to detect directly because they emit so little. The lensing geometry ruled it out, and did so cleanly. Filament lensing produces a distinctive elongated shear pattern aligned with the filament axis, because the mass itself is arranged as a thread, and the distortion inherits that directionality. The Webb signal showed no such elongation. It was close to circular in projection, with no preferred axis. The mass reconstruction that a filament produces, and the mass reconstruction that appeared in the data, are not similar objects that require careful discrimination. They are different shapes. The third candidate was a chance fluctuation in the distribution of dark matter, a random clumping along the sightline that happened to produce a lensing signal without any structure being present in the usual sense. The problem here is magnitude. Simulations of large-scale structure tell you precisely how much clumping to expect at any given scale and distance, because that distribution is one of the primary outputs the models are validated against. Producing the observed signal by chance would require a dark matter concentration roughly 10 times denser than anything the standard model permits in that regime. The probability is not zero, but it is small enough that invoking it as an explanation requires more special pleading than the alternative it is being used to avoid. When your conservative explanation is less probable than your radical one, it has stopped being conservative. The fourth candidate was an instrumental artifact, a systematic in the alignment of the mirror segments, a subtle correlated error in the detector arrays, something in the optical path producing a false pattern that looks like shear. This was tested directly by examining other fields observed with the same mirror configuration, the same instrument, the same processing chain. If the pattern were an artifact of the optics, it would appear in those fields too, because the optics travel with the telescope. It did not. The signal was tied to a specific patch of sky, not to a specific state of the instrument. Repointing the telescope did not carry it along. It stayed where it was, in the sky, which is precisely the behavior of something real, and precisely not the behavior of an artifact. The fifth candidate was weak lensing noise, the cumulative effect of the many small deflections that light experiences from all the ordinary structure it passes on its way to us. These add up, and in principle they can occasionally conspire to produce a coherent-looking pattern where none exists. Statistical analysis of this effect established that it could not produce a signal with this combination of coherence, amplitude, and angular scale in a field this sparse. The whole point of a quiet field is that there is very little foreground structure to contribute, and the observed signal was well above what the accumulated noise from the known contents of that sightline could generate. 5 candidates, 5 failures, and they did not fail marginally, in the way that leaves room for a more careful analysis to rescue them. They failed on geometry, on amplitude, on detectability, and on reproducibility. What remained was a lensing profile that matches no known structure in the cosmological catalogue, produced by nothing detectable in a thoroughly surveyed region, with a geometry consistent with an extended planar surface rather than any localized concentration of mass. The elimination was complete, and the thing that had not been eliminated was the thing nobody could test with the data in hand. Something that is not part of our universe appears to be bending our light. Now, the history, because the theoretical framework that predicted this did not arrive last year. It has been in place for 4 decades, and for most of that time, the people who developed it were regarded as brilliant, mathematically rigorous, and quietly unemployable in observational cosmology. In 1983, a physicist named André Linde published work that took inflation in a direction most of his colleagues found uncomfortable. Alan Guth had proposed inflation a few years earlier, solving the horizon and flatness problems in one move, and the idea was rapidly gaining ground. Linde's contribution was to examine what happens when you treat the inflaton field quantum mechanically across the whole of the inflating region, rather than in a single patch. What he found was that the field's decay is not synchronized. In some places, it falls early. In others, it lingers. And while it lingers, those regions continue to inflate, generating volume at an exponential rate. The regions that stop inflating become universes. The regions that keep going become the background in which more universes will form. And because exponential growth outpaces everything, the inflating background always wins on volume, forever. He called it chaotic inflation. Later, when the implications had been more fully worked out, the framework acquired a blunter name: eternal inflation. The name captures the problem precisely, which is that once this process starts, there is no mechanism to stop it. It goes on producing bubble universes without limit into an unbounded future, and every one of those bubbles is causally sealed from every other. The reaction from the wider community was polite and dismissive in roughly equal measure. Nobody disputed the mathematics. The derivation was sound, and the reasoning was tight. The objection was philosophical, and it was a serious one. If the other bubbles are causally disconnected, then by construction we can never observe them, never receive a signal from them, never test their existence in any way. A theory that predicts only unobservable entities has stepped outside the boundary of science and into metaphysics, however elegant its equations. That criticism has force, and it should not be waved away. It was made by good physicists in good faith, and it dominated the field's assessment of eternal inflation for years. Linde kept working anyway. Others joined him. Alexander Vilenkin, who had arrived at overlapping conclusions independently. Alan Guth himself, who had proposed inflation in the first place, and who followed the logic where it led, despite being visibly unenthusiastic about the destination. Between them, they built out the mathematics of bubble nucleation, of how bubbles expand, of what happens when two of them meet, and crucially, they asked a question that changed the status of the whole enterprise. If bubbles can collide, and if our bubble collided with a neighbor at some point in its history, what would we actually see from the inside? That question has an answer, and the answer is not nothing. They calculated it. A low-energy collision, occurring far enough from our position that we survived it, would leave observable traces. In the microwave background, a roughly circular region of altered temperature, offset from the sky's center, with a specific profile across its boundary. In the large-scale structure of matter, a subtle asymmetry, a gentle distortion in how galaxies and voids are arranged in the affected direction. And in the geometry of space-time itself, near the boundary surface, a lensing signature with a characteristic extended profile that no concentration of mass could imitate. These predictions were in the literature by the 1990s. Almost nobody in the observational community paid attention, and it is not difficult to see why. The predicted effects were far below the sensitivity of any instrument then operating or planned. The theory carried a reputation for unfalsifiability that a set of technically correct but currently untestable predictions did little to dispel. Theorists working on eternal inflation were regarded, with a certain sympathy, as gifted people who had been seduced by the elegance of their own mathematics into a corner with no exit. Then the cold spot turned up. Roughly the right shape, roughly the right kind of anomaly, sitting in the oldest data we have. For a brief period, the ground shifted slightly. Then the supervoid was identified nearby. The consensus concluded that a mundane explanation was available, and the moment passed. The theorists were once again either wrong or, worse, not demonstrably right. They kept refining. They sharpened the collision models. They worked out that if a collision had left a signature in the microwave background, it must also have left a gravitational one in the structure of space, a region of subtly modified curvature that would lens background light in a specific way. They calculated the amplitude. And then they noted, in the way that theorists do when they are describing something they do not expect to see in their working lives, that detecting it would require an instrument far beyond anything available. They needed Webb. They had no reason to expect Webb would ever be pointed at the right piece of sky. When the anomaly surfaced in the calibration data, among the first people contacted was a theorist who had spent more than 20 years working on exactly this class of signature. He was shown the reconstructed lensing profile. He was shown its angular position relative to the cold spot. By the accounts of people present, he was quiet for a while. Then he said that this was consistent with what they had predicted. There is a particular kind of professional life in which you are right decades before anyone can check, and you spend those decades being treated as a serious person working on an unserious problem. It is not a comfortable life. Being right at the end of it is a different experience altogether, and not necessarily an easier one. There is a reason that physicists with no appetite for speculation, no fondness for science fiction, and considerable professional incentive to avoid the topic, keep arriving at the multiverse against their own preferences. It is not that they find it appealing, it is that they cannot construct a route around it that does not involve abandoning something they have better reasons to keep. Let us lay the chain out explicitly, one link at a time, because the force of the argument is in its ordinariness. Every step is a mainstream position. Only the destination is controversial. Step 1. Inflation occurred. The evidence is the flatness of space, the uniformity of the microwave background across regions that could never have communicated, and above all, the detailed statistical structure of the primordial fluctuations, which inflation predicted before it was measured. This is the standard view. Step 2. Inflation was driven by a field with a high energy configuration, which decayed into the hot, dense state we call the Big Bang. This is what inflation means. There is no version of the theory without it. Step 3. The decay of that field is governed by quantum mechanics, and quantum processes are probabilistic rather than deterministic. This is not a contested claim about an obscure corner of physics. It is the central feature of the most successful theory ever constructed. Step 4. A probabilistic decay does not happen everywhere at once. It happens at different times in different places, which means some regions exit inflation while others continue. Step 5. Regions that continue inflating grow exponentially. Regions that exit do not. Exponential growth outpaces linear growth without limit, so the inflating volume always dominates, no matter how many pockets drop out of it. Step 6. Therefore, inflation never globally ends, and pocket universes continue to form without limit. 6 steps, and not one of them is exotic. The multiverse is not an additional hypothesis bolted onto inflation by people who wanted one. It is what you get when you refuse to bolt anything on and simply follow the standard theory to its conclusion. To avoid it, you must break one of those links, and every proposal for breaking one has so far required something more speculative than the conclusion it was trying to escape. Now, the next part is what makes the whole picture do real work, and it concerns what is inside each bubble. When the inflaton decays, the state it decays into determines the initial conditions of the universe that forms, and because quantum mechanics allows a range of decay outcomes, different bubbles inherit different initial conditions. Different initial conditions can mean different values for the fundamental constants of physics. That phrase deserves unpacking because it is easy to nod at and hard to actually absorb. The constants of nature are the numbers that no theory explains: the strength of gravity, the mass of the electron, the strength of the force that binds atomic nuclei, the strength of electromagnetism, the value of the cosmological constant. We measure them with exquisite precision and we plug them into our equations, and no framework we possess tells us why they take the values they take rather than any other values. They are, in the current state of knowledge, brute facts. In the bubble picture, they stop being brute facts and become outcomes, local outcomes, the result of how the field happened to fall in this particular pocket. Ours are what they are because of an event in the first fraction of a second of our bubble's existence, and a different pocket, formed from a different decay, has different ones. And here is why that matters far more than it initially appears. Our constants sit inside an extraordinarily narrow window. Adjust the strength of the strong nuclear force by a few percent, and either the simplest nuclear reactions become impossible, or hydrogen fuses so readily that it burns away before stars can form. Adjust the mass difference between the proton and the neutron, and either free protons decay, or the universe fills with neutrons, and no chemistry ever happens. Adjust the cosmological constant upward by a modest factor, and space expands so quickly that matter never gathers into anything. Adjust it downward, and everything recollapses before the first star ignites. Almost every direction you can move in the space of possible constants leads to a universe that is empty, or that collapses immediately, or that is filled with a uniform structureless sludge in which nothing ever assembles. The window that permits stars, chemistry, planets, and eventually anything capable of noticing that it exists, is narrow in a way that has troubled physicists for as long as they have been able to calculate it. There have been two broad responses to this. One is to hope for a deeper theory that derives the constants uniquely, showing that they could not have been otherwise. Decades of effort have gone into that hope, and it has not been rewarded. The other is to accept that the constants vary from place to place, that most places are sterile, and that we necessarily find ourselves in one of the rare hospitable ones because there is nowhere else we could have found ourselves. It is not an explanation of why the constants are hospitable, it is an explanation of why we are looking at hospitable ones. That second response requires a multiverse, which is precisely what eternal inflation delivers, whether or not anyone ordered it. And now we come to the part of this that connects to the single most embarrassing number in physics. For a quarter of a century, dark energy has been the field's most uncomfortable problem. And it is uncomfortable not because it is poorly understood, but because our best attempt at understanding it fails by a margin that is difficult to state without sounding like a joke. Start with what we know. The universe is not merely expanding. The expansion is accelerating. This was established in the late 1990s by two independent teams measuring distant supernovae, both of whom expected to find the expansion slowing under gravity, and both of whom found the opposite. Distant galaxies are receding faster now than they were, as though something is pushing space apart from within. Whatever that something is, it accounts for roughly 68% of the total energy content of the cosmos, and we call it dark energy for the same reason we call anything dark, which is that the name is a placeholder for our ignorance. The natural candidate is the energy of the vacuum. Quantum field theory says that empty space is not empty. Fields fluctuate even in their lowest state, and those fluctuations carry energy. Empty space therefore has an intrinsic energy density, and that energy would behave exactly like dark energy, driving accelerated expansion. So the theory has a mechanism. The trouble is the number. When you calculate the vacuum energy density that quantum field theory predicts and compare it to the value we measure, the two disagree by something in the region of 120 orders of magnitude, a 1 followed by 120 zeros. There is no way to soften that. It is not a discrepancy in a difficult calculation. It is the largest gap between prediction and observation in the history of the subject, by an enormous margin, and it has been sitting there, unresolved, while everything around it was refined to extraordinary precision. Physicists call it the cosmological constant problem. They have been calling it that for decades, and it remains exactly where it was. What makes it worse is the character of the observed value. It is not zero, which would be strange, but at least suggestive of some symmetry principle forcing exact cancellation. It is very small and non-zero, which is far harder to explain because it requires the enormous predicted contributions to cancel against one another to something like 120 decimal places and then stop, leaving a tiny residue. No known mechanism does that. A cancellation that precise, terminating at exactly the right point, looks less like physics than like a coincidence nobody can account for. Here is where the bubble picture enters, and it enters in a way that could change the shape of the entire problem. One of the predictions of the bubble universe framework is that the boundary between two adjacent universes is not energetically neutral. The domain wall carries energy density. That energy is a real physical quantity determined by how different the two field configurations are, and it does not remain confined to the wall in an idealized mathematical sheet. It has gravitational consequences for the space around it. Its influence extends into the interior of each bubble, decreasing with distance from the boundary, the way the warmth of a wall extends into a room. From inside, that influence would not look like a wall. It would look like a small, diffuse, roughly uniform energy density permeating space, with no local source you could point to, driving expansion. Which is to say, it would look exactly like dark energy. The proposal, and it should be labeled clearly as a proposal rather than an established mechanism, is that what we measure as dark energy might not be intrinsic to our universe at all. It might be borrowed. It might be the gravitational influence of a neighboring universe's boundary bleeding through the wall that separates us, contributing a vacuum energy term that is small precisely because the boundary is distant and the effect falls off with distance. Consider what that would do to the cosmological constant problem. Currently, the problem is that we require an unexplained cancellation to 120 decimal places with no mechanism to produce it. Under this proposal, the observed dark energy density would not be a residue of a failed cancellation at all. It would be a separate quantity with its own natural scale, set by two computable parameters, the energy density of the domain wall and our distance from it. That does not dissolve the vacuum energy problem. The enormous contributions from quantum field theory still have to go somewhere, and whatever suppresses them remains unexplained. But it changes the question from why is this number so absurdly small to what sets this number, and the second question has a shape that physics knows how to attack. It replaces a miracle with a measurement, and there is a consequence that follows immediately and is genuinely startling. If the dark energy interpretation is correct, then the value of dark energy is telling us how far away the nearest boundary is. We have been measuring the distance to the edge of everything for 25 years without knowing that was what we were doing. The Webb signal sits in a region of sky where the domain wall models place the nearest boundary. If those models are right, then that anomaly in a calibration field is not a curiosity about cosmic structure at all. It is a direct sighting of the thing that has been quietly setting the expansion rate of our universe since before there were galaxies in it. The universe is not smooth, and the shape it does have is one of the most impressive confirmations the Standard Model has ever received. On the largest scales, matter is organized into a structure that took decades of surveying to recognize. Galaxies gather into groups. Groups gather into clusters. Clusters sit at the nodes of a network connected by filaments, long threads of dark matter and gas stretching across hundreds of millions of light-years. Between the filaments lie voids, enormous regions of relative emptiness that can span 300 million light-years or more, and that occupy most of the volume of the cosmos. This is the cosmic web, and its existence is a triumph. Take the tiny density fluctuations imprinted on the microwave background, let gravity act on them for 13 billion years in a computer simulation, and the cosmic web assembles itself. The filaments appear, the voids open up, the clusters condense at the intersections. When you compare simulated volumes to real galaxy surveys side by side, the correspondence is close enough that people who work with both have to check the labels. Almost nothing in science works that well, which is why a small deviation is worth noticing. 2 years before Webb launched, a survey paper examined the large-scale structure in the quadrant of sky that would later contain the anomaly, using galaxy position data from ground-based instruments. It was an ordinary paper doing ordinary work, cataloging voids and filaments and comparing them to simulation expectations. And in a footnote, in the section where authors record the things that did not quite fit and could not be pursued, it noted that the void distribution in that region showed a slight asymmetry inconsistent with the standard simulation at about the 2 sigma level. 2 sigma is nothing. It is the level at which working scientists say interesting and move on. In any large survey, features at that significance appear constantly, and almost all of them are noise. The footnote was appropriate, honest, and entirely unremarkable. Then the Webb signal appeared, and somebody remembered the footnote. The asymmetry was in the same direction, the same angular position. The voids on one side of that region were slightly larger than the simulations predicted. The filaments threading between them were slightly less dense. The overall pattern was of matter distributed as though something had been gently pulling it outward, toward the edge of the surveyed region, over a very long period of time. An external gravitational influence would do precisely that. A domain wall with non-zero energy density, positioned beyond the matter it is affecting, would exert a persistent pull on everything near it. Not a violent one, a drag, acting over billions of years, subtly biasing the assembly of structure in its direction. Voids nearest the wall would open slightly wider, filaments would stretch slightly thinner, clusters would end up marginally less concentrated than they should be. No single survey would ever catch that. It is far too small a distortion to identify against the noise of ordinary structure formation, and it would be dismissed as scatter every time. It only becomes visible when you already suspect where to look. So researchers did what you do at that point. They took 3 independent anomalies, derived from 3 completely different measurements using 3 completely different physical effects, and they overlaid them on a single map of the sky. The lensing signal in Webb's infrared data, the cold spot in the microwave background, the void asymmetry in the galaxy distribution. They aligned. Not perfectly. This needs to be stated plainly, because the temptation to overstate it is considerable. The uncertainties on each of the 3 positions are substantial. The cold spot is a diffuse feature in a low-resolution map. The void asymmetry is a 2 sigma wobble in a survey with its own systematics. The lensing reconstruction has error bars in both amplitude and position. Draw circles of appropriate size around each, and they overlap, but the circles are not small, and the probability of 3 independent anomalies aligning by chance is low without being negligible. It is the sort of number that would make a careful person raise an eyebrow rather than write a press release. There is also a version of this that any statistician will point out immediately, which is that we went looking for the alignment after knowing where the first anomaly was, and searches conducted after the fact are not the same as predictions made in advance. All of that is fair. What remains, after all of it, is a pattern, 3 separate windows onto the universe, measuring 3 unrelated physical quantities, each showing something slightly wrong in the same corner of the sky. In the history of this field, that particular configuration has a track record. It is very often the first sign that something real is present and has not yet been named. The cosmic web bends around things that exist. Something in that direction appears to have been quietly shaping it for a very long time, and whatever it is, it does not appear in any catalogue of our universe's contents. Which brings us to a part of the story that is not about physics at all. It is about people and institutions, and what actually happens when a small group of researchers finds themselves holding a result they did not want. Science is supposed to be self-correcting, and it is, but the correction happens through a social process staffed by human beings with careers, reputations, and a finite tolerance for professional risk. That process works remarkably well over decades. Over months, it can be considerably messier. The team was small, a handful of analysts, a couple of senior astronomers, and a theorist brought in as a consultant once the conventional explanations began collapsing. None of them had set out to find anything. They were checking a calibration field, which is the astronomical equivalent of verifying that the scales read 0 before weighing something. The discovery was accidental in the most literal sense available. Their internal process, by every account, was careful to the point of tedium. Every alternative was documented, every test was recorded, including the ones that produced nothing. By the time the standard catalogue of explanations had been exhausted, the case that something unusual was present in the data was solid. The case for what it was remained fragile. And those 2 facts pulled in opposite directions, which is the specific predicament that produces the decision they made next. They chose not to put the multiverse interpretation in the primary paper. That was deliberate, and it was strategic, and it was probably correct. Papers claiming extraordinary results attract extraordinary scrutiny, which is entirely appropriate, but scrutiny is not applied evenly. A submission proposing evidence of a neighboring universe arrives at a journal carrying assumptions before a referee has read the first line. The assumption that it is wrong. The assumption that there is an error somewhere and the referee's job is to locate it. The assumption that the authors have overreached. Under those conditions, a paper reporting a genuinely careful measurement can be rejected or revised into meaninglessness for reasons that have little to do with the quality of the measurement. So the primary paper described the anomaly and nothing else. An unidentified lensing signal with an unusual geometric profile in a well-characterized quiet field, inconsistent with every conventional explanation tested, with full angular, radial and spectral properties tabulated, and every null result reported. It made no claim about causes. It was rigorous, narrow, and almost aggressively unexciting. It was published. The interpretation went into a companion paper submitted some weeks later, with a broader author list including the consulting theorist and additional cosmologists who had spent careers on eternal inflation signatures. That paper proposed the domain wall reading and laid out the supporting alignment with the other anomalies. It ran into immediate resistance, and the resistance was not unreasonable. The referees raised legitimate objections. The measurement uncertainties were large. The domain wall models contain free parameters that can be tuned to fit a range of smooth profiles, which weakens the significance of any particular fit. The alignment with the cold spot and the void asymmetry was suggestive but had been identified after the fact. Every one of those is a real criticism, and every one of them would be raised by any competent reviewer doing their job properly. The paper went through 3 rounds of revision before a modified version was accepted, with the language considerably softened. The multiverse reading was presented as one possibility among several rather than as a conclusion. The hedging was appropriate. It was also, inevitably, the version that would attract less attention. The response in the wider community was quieter than you might expect, and quieter in a specific way that is worth describing. There was no public rejection. There was also no public embrace. Some researchers began discreetly checking their own datasets for anything corroborating. A few wrote critical responses. Most adopted the position that costs nothing and commits to nothing, which is to wait for better data and reserve judgment. That silence was not a verdict. It was the sound of a field that had not prepared for this and was trying to work out how to respond without anyone having to go first. And while the community waited, the data sat in the archive, unchanged, still unexplained, still pointing in a direction that everybody found uncomfortable and nobody could quite eliminate. Suppose it is real. Suppose the signal is what the domain wall theorists say it is. Then there is a consequence that follows immediately, and that is genuinely difficult to sit with, because it is not abstract at all. There is a somewhere on the other side, not an emptiness, not a void, not the absence of things, a region of space-time with its own contents, its own history, its own expansion, running under its own version of physical law, which has existed for as long as ours has existed, and possibly considerably longer, and the rules there are probably not our rules. In the bubble picture, each universe inherits its constants from the state the inflaton field was in when it decayed in that pocket. Different decay states give different constants. So the neighbor on the other side of the wall has, in all likelihood, a slightly different value for something fundamental. What would that mean, physically? It depends entirely on which constants differ and by how much, and the range of outcomes is enormous. If only the cosmological constant differs, the neighbor is a universe much like ours, in its microphysics, but with a different expansion history. Atoms would be identical, chemistry would be identical, stars would form and burn and die in recognizable ways. But space over there would be stretching at a different rate, and over billions of years, that single difference compounds. Structure might have assembled more efficiently, producing a universe denser with galaxies, or expansion might have outrun gravity, leaving a thin scattering of isolated islands in an ever-emptying dark. If a force strength differs, the divergence becomes fundamental. Change electromagnetism and electrons orbit at different radii. Chemical bonds have different strengths, and every molecule that can exist has a different shape and stability. Change the strong nuclear force, and the periodic table itself is rewritten. Elements stable here might be unstable there. Elements impossible here might be commonplace. Stellar fusion would proceed along different pathways at different rates. which means stars of different sizes with different lifetimes, producing different elements in different abundances, which means any planets that form are made of different stuff. Push far enough in most directions and you do not get an alien universe. You get no universe at all. You get a region that expands into nothing before matter can gather, or collapses before anything can happen, or fills with a uniform gas that never condenses into a single structure in its entire history. Which is what makes the stability of our own conditions look so peculiar once you can compare it against a landscape of possibilities. We have generally treated the laws of physics as a foundation, the thing beneath everything that simply is. In this picture, they are more like weather, a particular configuration that settled here for local reasons, which could have settled otherwise and elsewhere did. Now here is the part that is genuinely frustrating, and it is the honest center of this entire story. The signal tells us that something is there. It tells us roughly how far away the boundary sits. It tells us something about the energy density of the wall itself, because that energy is what produces the lensing we measure. It tells us almost nothing about what is on the other side. The boundary is a one-way information barrier, and not by accident. Light from the neighboring universe cannot cross it and remain interpretable as light on our side, because the physical constants governing electromagnetic radiation are different over there. What arrives, if anything arrives, would not be a signal in any form we could decode. The transition itself would transform it beyond recognition. We can establish that the wall exists. We cannot look through it. It is not a matter of building a better telescope. The obstruction is structural, but the theorists have not simply accepted that and gone home, and what they have been attempting is ingenious. The energy density of a domain wall is not arbitrary. It is determined by the difference between the field configurations on either side. A large difference means a high-energy wall, a small difference means a low-energy wall. That relationship runs in both directions, which means the wall's energy is a measurement of how far apart the two universes are in the space of possible configurations. And the Webb signal implies a low-energy wall. The lensing effect is subtle. If it were a high-energy boundary, the distortion would be dramatically stronger and would almost certainly have been detected long ago by less capable instruments, or would have destroyed the region entirely. Low energy means the two field configurations are close together. Close together in configuration space means similar constants. If that reasoning holds, then the universe on the other side of that wall is not an incomprehensible alien realm operating under laws we could never imagine. It is probably close to ours. Recognizably so, a place where atoms form and stars ignite and galaxies assemble, running on slightly different numbers, arriving at a slightly different result. Whether anything inside it is looking outward, wondering about a faint distortion in its own sky, is a question with no available answer, and possibly no answer at all. Now let me bring in something that will make some viewers uncomfortable, because it deserves a proper hearing and because it becomes strangely relevant here. Every few years, a philosophical argument resurfaces that professional physicists find irritating in proportion to how difficult it is to dismiss. It goes as follows. If it is possible to simulate a universe in sufficient detail that entities inside the simulation could not detect their situation, and if civilizations tend to reach a level of capability where such simulations become feasible and cheap, then over time, the number of simulated universes will vastly exceed the number of base-level ones. And if that is the case, then any observer choosing at random which one they are in should conclude they are almost certainly inside a simulation. This is the simulation argument, formalized by the philosopher Nick Bostrom in 2003. Most working cosmologists find it more interesting than convincing, and treat it as a thought experiment rather than a hypothesis, largely because it makes no distinctive testable prediction. Then Webb found something at the edge of the observable universe that looks like a boundary, and the argument acquired a strange new relevance. Here is the first reading. If we are inside a simulation, it has limits. Computation is finite. A universe rendered in full detail at every scale at every location simultaneously is not feasible even in principle, given what we understand about information density and processing. An efficient simulation would render in detail only what is being observed, and handle the remainder at lower fidelity or not at all, and any such system would have edges, places where the rendered region terminates, and those edges might leave detectable artifacts, anomalies that do not follow from the internal physics. A domain wall at the boundary of the observable universe fits that description with uncomfortable ease, a place where the physics engine transitions between regions, a seam in the rendering. Under this reading, the lensing profile is not the boundary of a bubble universe, it is the boundary of the simulation. This is not falsifiable and it should not be presented as science. But it is worth noting that it is not obviously less consistent with the data than the bubble collision hypothesis. Both frameworks predict a boundary, both predict anomalous lensing, both predict an extended surface at cosmological distance. They are, at the level of what we can currently measure, difficult to tell apart. Here is the second reading, which is less comfortable and more interesting. The bubble hypothesis says, our universe exists inside a vastly larger, inflating background, surrounded by other universes we can never observe or reach. That is a description of containment. Our observable cosmos is not the whole of things. It is a region inside something bigger. The simulation hypothesis says our universe exists inside a constructed system that encompasses it, run by processes we cannot access or perceive. That is also a description of containment. Structurally, these are the same claim. One says the container is physical, and the other says it is computational, and it is not obvious that the distinction is as significant as it first appears, or even that it is well defined. What matters, in both cases, is the containment itself. Because whichever reading you prefer, the observation carries the same implication. Our observable universe is not everything. It is a portion of something larger that we cannot fully access. That conclusion does not depend on picking a framework. It follows from the data. The universe we believed we lived in, complete and self-contained, running from a beginning to whatever end awaits, mapped and modeled and measured edge to edge, may be something more like a room, and Webb may have just found the wall. Which brings us to string theory, and to the most remarkable reversal in this entire account. String theory has a reputation problem, and it is deserved. It is the most mathematically sophisticated framework physics has ever produced. It has consumed the working lives of some of the most capable people in the field for half a century, and it has not produced a single confirmed, unique, testable prediction about our universe. Not one. The obstacle has always been the same. String theory does not have a solution. It has solutions, in a quantity that defeats intuition. The number usually quoted is around 10 to the power of 500. For scale, the estimated number of atoms in the observable universe is around 10 to the 80th. The count of possible string vacua exceeds the count of atoms in everything we can see by a factor so large that comparison stops conveying anything. Each of those solutions describes a possible universe with its own particle content, its own force strengths, its own geometry of the compactified extra dimensions the theory requires. The full space of them is called the landscape. For decades, the landscape was regarded, by critics and by a fair number of practitioners, as a fatal problem. A theory that permits everything predicts nothing. If any configuration of constants is allowed, the framework has no power to explain why we observe ours. Enormous effort went into finding a selection principle, some mechanism that would single out our vacuum from the 10 to the 500 alternatives. None was found. What emerged instead, once string theory was combined with eternal inflation, was that the selection mechanism might not be theoretical at all. It might be physical. Eternal inflation samples the landscape. Every bubble that nucleates corresponds to one point in it, one configuration the fields fell into when they decayed in that pocket. The landscape is not a mathematical embarrassment listing universes that could have been. It is a map of what actually exists somewhere. That reframing changed the landscape from a failure into a source of predictions. If the landscape is physically realized, then other universes exist with different constants. They are separated from ours by domain walls. Those walls have energy densities computable from the structure of the landscape itself, and a universe near such a wall would observe specific consequences: a boundary lensing signal, a cold spot in the microwave background, a subtle asymmetry in large-scale structure. When the Webb signal surfaced, the landscape community was among the first to produce quantitative analyses because the machinery was already built and had been sitting idle for years. Domain wall energy densities, boundary lensing profiles, microwave background imprints, all of it calculated and published, waiting for something to compare against. The comparison was not decisive. Webb's uncertainties are substantial, and the landscape models carry enough free parameters that fitting them requires care and honesty about what a fit is worth. But the order of magnitude agreement was there. The lensing amplitude, the angular scale, the profile shape, all consistent with a domain wall at the implied distance. String theory has been accused of unfalsifiability precisely because the landscape can absorb any observation. That criticism is fair, but there is a meaningful difference between a framework that accommodates a result afterward and a framework that specified the type and scale of a signal beforehand, in papers published before the instrument that found it had left the ground. That is not proof. It is the first time in 50 years that string theory has been in the position of having said something specific in advance and then watched the sky appear to agree. Nobody has ever been to the edge of a universe, and in classical physics the phrase barely passes. Space is continuous and unbounded. There is no rim, no surface, no place where you run out of somewhere to go. Travel far enough in any direction and you simply find more of the same. But in the framework this signal points toward, the edge is not a location in space in the ordinary sense. It is a transition in the structure of space-time itself, and asking what would happen there is a legitimate physics question with a partial answer. The domain wall is not a barrier in the way a physical object is a barrier. It does not push back. It is a region where a field is transitioning between two stable configurations, high on the ridge between two valleys, on its way from the value it holds throughout our universe to the value it holds throughout the neighbor. The thickness of that transition depends on the energy difference between the two states, and for a low-energy wall of the kind this signal implies, the transition zone could be extraordinarily thin, possibly approaching the Planck length, around 10 to the minus 35 meters, which is the scale at which the concept of distance itself becomes questionable and our theories stop functioning. For every practical purpose, then, the boundary has no thickness. There is no crossing in the sense of a journey through something. There is a here and then there is a there, with nothing in between. What would happen to an object at that transition? And let us be clear that this is entirely hypothetical, since the boundary sits 11 billion light-years away, and traveling there is not a coherent proposal, depends on what changes. If only the cosmological constant differs, the immediate consequences are subtle to the point of imperceptibility. Space would expand at a marginally different rate. Nothing local would register. Matter would behave normally. Chemistry would proceed. Only across astronomical timescales would the difference compound into anything observable. If the force strengths differ, the consequences are immediate and comprehensive. Atoms are not fundamental objects. They are dynamic equilibria, arrangements held in balance by the competing pull of electromagnetism and the strong nuclear force and the exclusion behavior of electrons. Change any of those inputs and the equilibrium shifts. Electron orbitals would reconfigure. Nuclei that were stable would begin to decay, and nuclei that were unstable might settle. Every chemical bond in every molecule would find itself at the wrong energy for the new rules. An object crossing that boundary would not be destroyed by an impact. It would be dismantled by the arithmetic. Its constituent particles, suddenly governed by different numbers, would cascade into whatever configurations the new constants permit, and the result would bear no relationship to what went in. For a low-energy wall, where the differences are small, The crossing might be survivable in a narrow technical sense. Matter would still exist. Atoms would still form. The laws would not have changed so violently that structure becomes impossible. But survivable is not the same as recognizable. An observer on the far side would find themselves in a universe running on adjusted rules, looking back at a boundary through which nothing can meaningfully return. And there is something deeper here that the physics obliges us to confront, and it is the strangest single fact in this whole account. The domain wall is not merely a physical boundary, it is a boundary of causality. Every event has a past light cone, the region of space-time from which anything could possibly have influenced it. Everything that has ever affected you in any way, every photon that has reached your eye, every gravitational pull, every particle, originated inside your past light cone. It is the totality of what could have mattered. Our past light cone does not extend across that wall. The neighboring universe has its own past light cone, and the two do not intersect. Whatever happened over there before the bubbles approached one another had no causal influence on anything here, and nothing here had any influence there. Two universes, adjacent in space, completely isolated in time, sharing a boundary and sharing nothing else. That is a stranger relationship than distance. Distance can be crossed given enough time. Causal disconnection cannot be crossed at all, by anything, ever, under any circumstances, no matter how much time is available or how advanced the traveler. It is not a limitation of engineering. It is a feature of the structure of space-time. So the edge of everything is not empty. It is occupied by the boundary of somewhere else, and that somewhere else has been sitting there, permanently beyond reach, since before our star existed, and since before the matter our star is made of had been forged in earlier stars. Now, having followed this interpretation as far as it goes, honesty requires that we go back and look at the alternatives properly, because the domain wall reading is not the only one on the table, and the others are not foolish. When a serious anomaly survives the first assault of skepticism, the field enters a phase that looks from outside like confusion, and from inside like competition. Multiple frameworks, multiple teams, multiple interpretations, all making different predictions about what future observations will show. The Webb signal has produced 3 serious readings. All 3 are compatible with the current data. All 3 make different forecasts, and none of them is comfortable. The first is the domain wall hypothesis, which we have now covered in detail. A bubble collision boundary at roughly 11 billion light-years, producing the lensing signal, the cold spot, and the void asymmetry as a single unified set of consequences from one physical cause. Its principal strength is that the predictions preceded the observation. The profiles were calculated and published before the instrument that measured them existed. That is the strongest form of scientific evidence available, short of direct detection, because it removes the possibility of a model being shaped to fit a result already known. Its principal weakness is what it costs. Accepting it means accepting that our universe is one of an unbounded number, that we are embedded in a structure we can barely measure and can never explore, and that the standard cosmological model is incomplete in a manner that cannot be repaired from within. That is an enormous bill, and extraordinary claims are correctly required to pay it. The second interpretation is modified gravity, and it deserves more respect than it usually receives in popular accounts. General relativity, for all its success, is a classical theory. It does not incorporate quantum mechanics consistently, and everyone knows it must break down somewhere. A family of extensions collectively called modified gravity alter how gravity behaves on very large scales, and some of these can produce lensing signatures that the standard theory cannot. Certain versions involving additional spatial dimensions, where gravity propagates into dimensions the other forces cannot access, produce extended planar lensing effects that resemble a domain wall signature closely enough that distinguishing them requires better data than currently exists. The appeal of this reading is obvious. It stays within a single universe. It requires modifying a theory we already know is incomplete, rather than introducing an entire ensemble of unobservable cosmoses. By any ordinary measure of parsimony, it is the more restrained hypothesis. Its weakness is that the specific modification required to fit Webb's data has to be tuned carefully and is not independently supported. Modified gravity theories are strongly constrained by other observations, from the solar system to binary pulsars to the propagation speed of gravitational waves, and the versions that survive those constraints do not naturally produce this signal. You can construct one that does, but the construction is not motivated by anything except the desire to fit this measurement, which is precisely the kind of maneuver that ought to make everyone suspicious. The third interpretation is the most conservative, and for that reason, the most difficult to dislodge. Unresolved large-scale structure. The argument is that the region may contain complicated arrangements of dark matter and ordinary matter, overlapping sheets, superimposed filaments viewed at unlucky angles, void boundaries stacked along the sightline, that current surveys have not resolved in sufficient detail to model. In combination, such structures could in principle produce a composite lensing signal that mimics the smooth profile of a wall. The appeal is that it requires no new physics of any kind. Everything involved is known to exist. The only claim is that we have not mapped it well enough, which is unquestionably true of most of the universe. The weakness is that it demands an improbable configuration in a region specifically selected and repeatedly verified as containing nothing unusual. And it has an additional problem, which is that this explanation must be invoked 3 separate times for 3 separate anomalies that happen to align. Unresolved structure could produce the lensing. Something else would have to produce the cold spot. Something else again would have to produce the void asymmetry. It explains each individually, at the cost of explaining their coincidence not at all. Every one of these readings has advocates and critics, and the exchanges in the literature have been notably sharp. This is not a field that rewards diplomacy when paradigms and careers are both in play. But notice what all 3 agree on. The signal is real. Nobody is arguing that the data is spurious or that the analysis is flawed. The disagreement is entirely about what kind of unusual thing is present, not whether one is. And that, historically, is exactly how the discoveries that mattered began. Dark energy was real before anyone had a name for it. The accelerating expansion was confirmed years before any mechanism was proposed. The Hubble tension has been solidly established for a decade with no consensus explanation and no sign of one. Something is there. 3 stories are competing to account for it, and one of them, if it prevails, redraws the boundary of the universe as our species understands it. The Big Bang is the most successful story science has ever told. A hot, dense beginning, an expansion outward, a cooling, a condensation into everything. It is elegant, it is supported by multiple independent lines of overwhelming evidence, and it has become the default picture of cosmic origins for educated people across the world. It may also be incomplete in a way that changes what it means. Be careful here, because there is a distinction that gets lost in popular accounts, and it matters enormously. The Big Bang model describes what happened to our universe from a very early hot, dense state onward. That model is not under threat. The microwave background, the abundances of the light elements, the growth of structure, all of it confirms that our universe passed through such a state and evolved from it. Nothing in this story questions that. What is in question is what produced that state, what set the initial conditions, what determined the temperature, the density, and above all the specific pattern of fluctuations that seeded every structure that would ever exist. In the standard account, the answer is quantum fluctuations in the inflaton field, stretched to cosmic scale by inflation, and frozen into the fabric of space. This works beautifully. The predicted statistical properties of the fluctuation spectrum match the measured pattern in the microwave background to impressive precision, and that agreement is one of the strongest pieces of evidence for inflation we have. But there is another process that produces a comparable spectrum, and it is not quantum noise. When 2 bubble universes collide, the event is not instantaneous, and it is not clean. The boundary between them does not simply form and settle. It oscillates, it rings, like a struck bell, and those oscillations propagate as waves of energy through the space-time of both bubbles, traveling inward from the point of contact across the interior. Those waves are not uniform. They carry structure, a spectrum of fluctuations determined by the dynamics of the collision, the energies involved, the geometry of the impact. Theoretical work over the past 15 years has established something remarkable about that spectrum. Under a range of plausible conditions, the fluctuation pattern produced by a bubble collision is indistinguishable from the pattern produced by stretched quantum noise. Not similar, not approximately alike, mathematically identical to within the precision of any measurement we are currently capable of making. If that result holds, and it is a theoretical finding rather than a confirmed observation, then the pattern in the microwave background that we have been attributing to quantum fluctuation could equally be the ringing of our own universe from an impact at or near its birth. Consider what that implies. The Big Bang would not be an expansion from a point in isolation, it would be the aftermath of a meeting. Our universe would have begun inside the shock of two bubbles pressing together, the collision energy converting into the heat and matter of the primordial fireball, the oscillation of the boundary imprinting the fluctuation pattern that would eventually become every galaxy, every star, every planet, and every person who would ever wonder about any of it. We would be the children of a collision. Every supernova that ever burned, every nebula that ever collapsed, every element heavier than helium, forged in stellar cores over billions of years, and every planet assembled from that debris, and every ocean, and every organism, and every thought that has ever occurred anywhere in our cosmos, set in motion by two expanding boundaries, meeting in the space between inflating regions, before there was anything here at all. And the signal Webb found at 11 billion light-years might be the boundary of the universe that hit us. The cold spot in Eridanus might be the echo of that impact, still ringing across our sky 13 billion years later, faint but never silenced. If any of that is right, then the Big Bang was never a beginning. It was a collision, and we are the wreckage, and the wreckage learned to look up. So how will we ever know? This is where the story turns from speculation towards something more concrete, because the answer is not never, and it is not eventually. The answer is that a set of instruments now coming online will settle it, and most of us will still be here. Science moves slowly by design. The verification of extraordinary claims requires evidence from multiple independent sources, gathered patiently before anyone is willing to update the picture of reality. That caution is not timidity. It is the mechanism that makes the whole enterprise trustworthy, and the history of physics is littered with compelling anomalies that turned out to be loose cables, analysis errors, or statistical noise that dissolved on closer inspection. Patience has saved this field from a great many embarrassments. But the tools arriving over the next decade will not require patience in the same way. They will be decisive. The first is the Vera Rubin Observatory in Chile, which will conduct the legacy survey of space and time. It is designed around a single principle, which is to image the entire visible sky repeatedly, night after night, for 10 years. Over its operational life, it will measure the shapes of tens of billions of galaxies with the precision needed to map weak gravitational lensing across the whole sky at a level of detail that no previous survey has come close to. And that is precisely the measurement this question requires. If the domain wall lensing signal is real, Rubin will not see it as a faint anomaly in a single calibration field. It will see it as a coherent feature in a full sky map, with enough signal to characterize the profile properly, measure the angular extent, and test whether the shape genuinely matches a planar boundary at cosmological distance rather than something more mundane. And if it is not real, Rubin will show that too. A statistical fluctuation or an artifact of unresolved structure does not survive being embedded in a survey of that scale. It will average out into the surrounding sky and disappear. A null result from Rubin would substantially weaken the domain wall hypothesis and shift the weight of evidence firmly toward the conventional explanations. That symmetry, The fact that the test can fail as clearly as it can succeed is what makes it a real test rather than a fishing expedition. The second instrument is Euclid, launched by the European Space Agency in 2023 and now in operation, mapping the three-dimensional distribution of galaxies across roughly a third of the sky. Euclid was built specifically to study dark energy and the growth of cosmic structure, which makes it almost perfectly suited to this question by accident. Its galaxy-shape measurements provide an independent test of the lensing signal using different optics, different detectors, and different systematics. And its three-dimensional maps will either confirm or eliminate the void asymmetry, that quiet footnote in a pre-Webb survey paper that has since acquired a significance nobody anticipated when it was written. The third instrument is Webb itself, pointed deliberately at the anomalous region, rather than glancing at it during a calibration exercise. With longer exposures and broader wavelength coverage, Webb could characterize the profile in far greater detail. The critical measurement is the radial falloff. A planar boundary produces a specific gradient. A mass concentration produces a different one. With sufficient exposure time, those two possibilities separate cleanly, and the question stops being interpretive and becomes arithmetic. Proposals for such observations have been submitted. Whether they succeed is not purely a scientific matter. Webb time is among the most contested resources in science, with proposals from every branch of astrophysics competing for a fixed number of hours, evaluated by committees weighing exoplanet atmospheres against galaxy formation, against stellar populations against this. Whether the field receives its dedicated observation depends on institutional judgment about which questions are worth the hours. There is something almost absurd in that. The question of whether our universe has a neighbor may be settled or shelved according to a review panel's assessment of scientific priority. But that is how the process actually works, and pretending otherwise would be dishonest. What is not in doubt is that the decade ahead will not merely refine this anomaly, it will resolve it. Either the signal strengthens as data accumulates, and the domain wall interpretation moves from a possibility that careful people mention cautiously into a serious candidate for the most consequential discovery in the history of cosmology, or it fades, and the universe remains, at least as far as we can observe, a single entity, 10 years, possibly less. The instruments are built. The only open question is whether the universe intends to answer. There is a consequence of all this that runs deeper than any particular measurement, and it concerns what we mean by a law of nature. Physics is built on the idea of laws, and not laws in the legal sense, which are conventions that can be amended by whoever holds authority. Laws in the older, harder sense, regularities that hold everywhere, at all times, without exception and without negotiation, the speed of light in vacuum, the conservation of energy, the relationship between mass and the curvature of space-time. These are the flaw beneath every calculation anyone has ever performed. They are what makes science possible in the first place, because they carry an implicit guarantee that what you discover here will hold there, that an experiment performed in one laboratory tells you something about every other place and every other time. Without that guarantee, science is not a way of understanding the universe. It is a way of cataloguing local curiosities. The bubble universe picture does not break that guarantee within any single universe. Inside our bubble, the laws are constant, the constants hold, and every experiment ever performed remains as valid as it was yesterday. Inside the neighboring bubble, the laws are equally constant, just constant at different values. Each universe is internally coherent. Each is governed by regularities that an observer inside it could discover, rely on, and build a civilization upon. But step back and view the landscape entire, the full ensemble of universes, each with its own settings, and there are no universal laws at all. There are only local ones. The regularities that hold here are not features of reality. They are features of this region of reality, and other regions have their own, incompatible with ours and equally binding within their borders. That is philosophically destabilizing in a way that takes time to absorb properly, and I want to be careful about the size of the claim. Science currently assumes, and has always assumed, that what we find here applies everywhere. We test this constantly, without announcing that we are testing it. Every time we analyze light from a distant galaxy and find that hydrogen there produces exactly the spectral lines that hydrogen produces in a laboratory on Earth, we are confirming that atomic physics is the same 11 billion light-years away. Every time we observe a distant supernova detonating at exactly the brightness that nuclear physics predicts, we are confirming that nuclear physics holds across the observable universe. These tests pass. Constantly, everywhere we look. The universality is real, and it is measured. But it is measured inside our bubble. Every observation we have ever made in the entire history of our species comes from inside a single pocket. Our sample size, in the relevant sense, is 1. A philosopher of science would identify this as a problem of induction, and it is the oldest problem in the discipline. We inferred universal laws from local observations, and the inference was sound within the domain we sampled. If the laws vary between bubbles, then our reasoning was correct in its domain and overreached in its conclusion. We discovered the laws of our universe. We believed we had discovered the laws of the universe. That distinction is not a technicality, it is the whole thing. What rescues science in this picture is locality rather than universality. The laws hold here, they hold everywhere within our bubble, which extends far beyond anything we will ever observe. Predictions still work. Bridges still stand. Spacecraft still arrive where the equations say they will. The flaw did not vanish. It turned out to be a flaw with edges, in a building we cannot leave. The crisis is not practical. It is foundational, and it lands on one specific question. Why are the constants what they are? That question has driven a great deal of theoretical physics for a century, and the hope has always been that a sufficiently deep theory would show that the constants could not have been otherwise, that they follow necessarily from some principle we have not yet found. In the bubble picture, that hope is misplaced, because there is no answer of that kind. The constants are what they are because this is where we happen to be. Other pockets have other values, equally arbitrary, equally unexplained, equally satisfying to whatever observers exist inside them. The Webb signal, if it is real, does not merely enlarge the universe. It contracts the meaning of the laws we thought we had found. It suggests that some part of what we have been calling physics may turn out to be geography, and that lands somewhere very close to home, which brings me to the part of this that is not about equations at all. Cosmology can feel disconnected from ordinary life. The distances are too large to picture. The timescales do not fit inside a human being. The existence of other universes separated from ours by a wall, 11 billion light-years away, can seem like the kind of knowledge that is interesting for an evening and changes nothing at all about tomorrow. That reaction is fair, and it is also incomplete, because this touches something people have been circling for as long as there have been people. Across every culture and every tradition, in every form of thought that has ever been recorded, human beings have asked whether we are alone, whether this world is singular, whether the universe is a stage arranged with us in mind, or a vast indifferent process in which we are an accident, or something else entirely that our available concepts have never been adequate to describe. The existence of other universes does not answer the question of life elsewhere. That is a separate question, and it stays inside our own bubble, where the search continues with instruments of its own. But it changes the frame around the question in a way that is difficult to shake off once you have seen it. We were asking whether we are alone in the universe. If our universe is one pocket among an unbounded number, each with its own constants, its own history, its own potential for complexity, then the question expands to something else entirely. Whether anything, in any bubble, under any set of laws, has ever assembled itself into structure, and then into complexity, and then into awareness. And the answer to that, given the size of the ensemble, is almost certainly yes. The landscape is too vast. and the conditions for complexity too loosely constrained for ours to be the only pocket that ever produced anything. Other bubbles with constants close enough to permit stable matter and chemistry almost certainly exist somewhere in that unbounded set. Whether they ever produced observers is unknown. Whether those observers, if they exist, will ever know anything about us is not merely unknown but permanently unknowable, and that permanence is the part that sits strangely. There is grief in this for some people, and it should not be dismissed. The universe we believed we occupied, the single complete self-contained reality that began with the Big Bang and would end in whatever final state awaits, was in this picture never quite what we thought. It was always a region, a pocket, a local outcome of a process older, larger, and stranger than anything our ancestors or our physicists imagined. Something that felt like a cosmic home, ours entirely, edge to edge, becomes instead one room among an endless number, surrounded by others we can never enter and whose occupants we can never meet. But there is something else alongside the grief, and I think it is the larger thing. That signal, faint and precise and geometrically impossible by everything we believed we knew, is evidence that reality is bigger than our imagination had allowed, that it is richer, stranger, and more deeply structured than any model we had built to contain it, and that the act of looking carefully at the sky, with sufficient precision and sufficient patience, can reveal not only what is inside our universe, but the shape of what lies beyond it. We are not at the center of our solar system. We are not at the center of our galaxy. We are not at the center of our universe. And we may not be inside the only one there is. That is not a diminishment. Every previous step in that sequence felt like one at the time and turned out to be the opposite. It is an expansion of what it is possible to know. Not every response to this has been measured, and it would be dishonest to pretend otherwise. Cosmology is a human enterprise. The people who built the Standard Model, who spent careers refining lambda cold dark matter, who developed the mathematics of the microwave background and constructed the structure surveys and hunted down the systematics in the Hubble measurements, invested more than working hours. They invested intellectual identity. The framework they built is not a collection of equations. It is a coherent picture of what the universe is, assembled over a century by thousands of people, and it works. When a picture like that is challenged at its foundation rather than at its margins, the response is not purely scientific, because the people responding are not purely scientific instruments. Several prominent defenders of the single universe reading have been vocal in their skepticism, and their objections are legitimate. The uncertainties are large. The models have free parameters. The alignment of independent anomalies could be coincidence and was identified after the fact. These are real concerns raised by serious people doing exactly what the process requires them to do. The case for the bubble interpretation is suggestive, not conclusive, and anyone claiming otherwise is overselling it. But some of the pushback has a different character. The argument that a neighboring universe is simply too improbable to entertain, regardless of what the data shows, is not a scientific argument. It is an aesthetic preference dressed in scientific language, a preference for a simpler cosmos, a single cosmos, one whose boundaries lie entirely within reach of human investigation. That preference is deeply understandable. It is also, if the data holds, a preference the universe is under no obligation to share. There is a real poignancy in the position of researchers who have spent decades working productively within the Standard Model, producing results that are genuinely important and genuinely correct within their domain, only to find that the domain itself may be smaller than they believed. Their work is not invalidated. General relativity still holds inside our universe. Dark matter still shapes the cosmic web. The acoustic oscillations still produce the fluctuations in the microwave background. All of it remains true, and all of it remains theirs. What changes is the frame around the picture. The universe those people spent their lives describing is exactly where they left it. It is simply not everything. For someone whose deepest intellectual commitment has been to understanding everything, to completing the picture of all that exists, discovering that the picture has a frame, and that there is something on the other side of it, is not a small adjustment. The history of science is a sequence of exactly these moments. The moment Earth stopped being the center, the moment the Sun became one star among billions, the moment our galaxy became one among hundreds of billions in a universe vastly larger than anyone had imagined. Every one of those expansions was resisted, sometimes fiercely, by capable people whose life's work had been built on the previous picture. Every one of those resistances eventually gave way, not because the resistors were persuaded, but because the evidence accumulated until the questions stopped being open. The people pushing back, now, are not wrong to push back. That is the job. Without skeptics, extraordinary claims would escape the scrutiny that makes the ones that survive worth believing. The process needs them, and it would be worse without them. But the data does not negotiate. It has no interest in careers or paradigms, or the elegance of a framework that took a century to build. It makes no allowance for intellectual investment, however deep and however legitimate. It simply is what it is, regardless of what any of us would prefer. So let us come back to where we started, because we have traveled a considerable distance from it. A calibration field, a patch of sky chosen for its emptiness. A telescope checking that its instruments read 0 and finding instead a shape. We have walked through the failure of every conventional explanation, one by one, on geometry and amplitude and detectability and reproducibility. We have traced the mathematics of eternal inflation and the bubbles it demands whether anyone wants them or not. We have followed 3 independent anomalies, measured by 3 unrelated techniques, converging on the same corner of the sky. We have looked at the shape of the signal itself, the extended planar profile that matches a domain wall and matches nothing else in the entire catalogue of things our universe is known to contain. We have listened to theorists who predicted exactly this signature decades before anyone could look for it, and who spent those decades being treated as brilliant people working on an unanswerable question. And we arrive, at the end of all of it, at a question that Webb cannot answer, that Rubin cannot answer, that Euclid cannot answer, that no instrument anyone has designed or imagined will ever answer, not because of the limits of our engineering, but because of the structure of reality itself. What is on the other side? Beyond that boundary, past the surface, where the field transitions out of the configuration our entire universe settled into, there is a region of space-time. It has existed for at least as long as we have. It is governed by laws close to ours but not identical. It is expanding on its own schedule, assembling its own structure, running its own history according to numbers that were set in the first instant of its existence by an event we cannot observe, and we cannot see it. We cannot signal it. We cannot receive anything from it. The boundary is causally opaque, and not because we lack the technology. Information cannot cross it in any form that would remain interpretable, and no future instrument changes that, because the obstruction is not in the instrument, it is in the geometry. Whatever is over there has been there, in total isolation from us, and we from it, since the first moment either of us existed. That is the silence this signal leaves behind. We found the wall, we measured its distance, we characterized its energy, we traced its effects on our light, on our structure, on the oldest picture of our sky. We built the theoretical framework that explains why it is there and what it separates. And at the end of all that work, we are standing at a boundary we cannot cross and cannot see through, knowing that something is on the other side, and knowing that we will never know anything more about it than that. That is not a failure of science. It is the discovery of a limit, and limits in physics have a habit of being the most important things we ever find. The speed of light is a limit, and it gave us relativity. The Planck scale is a limit, and it pointed toward quantum gravity. The cosmic horizon, the distance beyond which expansion carries objects away faster than their light can reach us, is a limit, and it led us to inflation. Every one of those, at the moment of its discovery, looked like a door closing. Every one of them turned out to be a door opening onto a larger room. The domain wall, if it is real, is a limit of a kind we have never encountered. Not a limit of speed, or of scale, or of resolution. a limit of causal connection, a place where our universe ends and something else begins, something described by the same equations. Something that has been running in parallel, separately, since before our star existed and before the atoms in our bodies had been assembled inside earlier stars. And on the far side of that boundary, separated from us by a surface thinner than an atom and further away than any mind can genuinely hold, the answer to the only question that matters is sitting exactly where it has always been, perfectly intact, perfectly silent, 11 billion light-years away, and permanently out of reach. The data came back wrong. It was never wrong. It was the first thing anyone has ever seen that came from the other side of the wall.